Hey everyone! Today, we're diving into one of the most popular unsupervised learning algorithms in machine learning, k-means clustering. Most of the time, we just call k-means from libraries and move on. But to truly understand how it works, how it handles centroids and minimizes distance, you need to build it yourself. By the end of this video, we'll have a fully functional Python class that can cluster data points just like the professional libraries do. Before we code, let's look at the 4 simple steps k-means follows. 1. Initialization. We pick k random points from our dataset to act as our initial centroids or cluster centers. 2. Assignment. We look at every single data point and calculate its distance to those centroids. Each point joins the cluster of the centroid it's closest to. 3. Update. Now that we have groups, we calculate the average of all points in each group. This average becomes the new location of our centroid. 4. Repeat. We repeat the assignment and update steps until the centroids stop moving significantly. This is what we call convergence. Choosing the right k is a huge topic. We usually use things like the elbow method to find the perfect number of clusters. I'm going to dedicate a whole separate video to those later, so stay tuned for that. All right, let's get our hands dirty with the code. We're building our k-means class from the ground up. I'll explain every NumPy trick we use to keep this efficient. First, we initialize our hyperparameters. We need k for the number of clusters, max_iters so we don't loop forever if the data is messy, and tol, which is short for tolerance. If our centroids move less than this amount, we consider the model converged and stop early. We also set self.centroids and self.labels underscore to none since they only exist after we see some data. Our first helper method is _init_random. K-means is sensitive to where it starts, so we need to pick k random points from our dataset X to act as starting centroids. We use np.random.default_rngparens.choice. By setting replace equals false, we ensure we don't accidentally pick the same data point twice to be a centroid. This is where the math gets interesting. For every point, we need to find the closest centroid. Instead of writing a slow for loop, we use vectorization. Notice this line. By adding a new axis to X, we're telling NumPy to compare every row in X against every centroid simultaneously. Then, this function with axis equals 2 calculates the Euclidean distance. Finally, np.argmin returns the index of the smallest distance. That index, 0, 1, or 2, becomes our cluster label. Once points are assigned, the centroids need to move. We use np.zeros underscore like to create a fresh template of zeros with the exact same shape. Then we loop through each cluster C. We use Boolean indexing. X labels equals to C grabs only the points belonging to that specific cluster. We then call .meanAxis equals 0 on those points. This calculates the average position in our multi-dimensional space. That average becomes the new centroid. If a cluster somehow ends up empty, we just keep the centroid where it was to avoid errors. Now we tie it all together in the fit method. This is what the user actually calls. 1. We convert X to a NumPy array using np.asArray to ensure we're working with floats. 2. We call our random initialization. 3. We start our main loop. In each iteration, we assign labels and update centroids. 4. The convergence check, we calculate the shift, the distance between the old and new centroids. If that shift is smaller than our tolerance, we break the loop early. This saves a lot of computation time. 5. Finally, we store the final labels in self.labels underscore. The predict method is actually quite simple. Once the model is fitted, we have fixed centroids. To predict a cluster for a new point, we just run it through assign labels. It finds the nearest existing centroid and tells us which group that new point belongs to. Let's test this on some synthetic data using make_blobs. We'll set k equals 4 and see if our algorithm can find the natural groups. Look at that! The black X markers are our centroids, and you can see they've settled right in the center of the data clouds. And that's k-means from scratch. We've gone from random initialization to a converged clustering model. Now remember, we assumed k equals 4 because we knew how many blobs we created. In the real world, you won't always know that. In the next video, I'll show you exactly how to use the elbow method to mathematically determine the best number of clusters for your data. If you found this helpful, hit that like button and subscribe so you don't miss the next one. The code is in the description. Happy coding!